Hello, this is the start of Chapter 6, Modeling Random Events and Using the Normal Distribution. The learning objectives for this chapter is being able to distinguish between discrete and continuous valued variables, and know when a normal model is appropriate and be able to apply the model to find probabilities. So first up, the different probability distributions. So a random variable, if we were to roll a fair die, the possible outcomes are the numbers 1, 2, 3, 4, 5, and 6, and each of these numbers has a probability of 1/6. Then rolling a die is a probability experiment whose outcomes are numbers, and the outcome of such an experiment is called a random variable. And here's just a shortened definition of the random variable. A random variable is a numerical outcome of a probability experiment. So we have two different random variables. We have discrete and continuous ones. Discrete random variables are random variables whose possible values can be listed. So examples of that include the number that comes up on the roll of a die, the number of siblings a randomly chosen person has, and how I think of discrete random, whether it's a discrete random variable, is they can be like a number or an integer like 0, 1, 2, 3, and not a decimal. While we have continuous random variables that are random variables that can take on any value in an interval, and examples of this are the height of a randomly chosen college student. They could be 5'11" and 3/8, 5'11" and 6/8. They can be 6'1" and 7/8. So there's definitely a continuous spectrum that they can take on. And then the amount of time a randomly chosen customer spends in the store. So they could be there for 8 minutes and 37 seconds, or 15 minutes and 32 seconds, or 25 minutes and 12 seconds. You can see it's kind of a continuous, not like a, hey, it's just this integer 25 or 15 or 10. So I would like for you to pause the video at this time to be able to figure these out. So here we're supposed to classify the following as discrete or continuous. So the length of the left thumb, well, I don't think there's like a 2 inches, 3 inches, 0 inches, 1 inch. It's going to be like 2 inches and 3/8 or whatever, so it's got to be continuous. The number of cars owned by a household, well, that's got to be integer, so it could be 0, 1, 2, 3, discrete. The number of devices in the house that connect to the internet, again, this has to be an integer, whether it's 0, 1, 2, 3, and that's discrete. And then the sodium concentration in the bloodstream. I'm not super familiar with how they measure sodium concentration, but I'm pretty sure it's continuous, because I'm sure there's probably like 0.3% concentration or whatever, and that could, so that's going to be continuous. So there's different probability models and distributions, and a probability model is a description of how a statistician thinks data are produced. So we have the uniform, the linear, the normal, and others. And a probability distribution or probability distribution function, PDF is what I'll call it, is a table, graph, or formula that gives all the outcomes of an experiment and their probabilities. So for this probability distribution, what is the probability of rolling a 5 or a 6? And we should know this from our previous chapter. So we're looking for the probability of a 5 or a 6. Well, 1/6 plus 1/6 again here. And we could, we don't have to subtract anything because rolling a 5 or a 6 are mutually exclusive, and that's just 2/6 or 1/3. 1/3. And then here's an example of a probability distribution graph, and this is also discrete, like the rolling die, it's discrete as well. Estimate the probability that a randomly selected reviewer gave this book a 3-star rating. So you could look at this number of stars, 3. Well, look at where the dot is, look to the left, so about a 10% gave this book a 3-star rating. And then discrete probability distributions. The most common way to display a PDF for discrete data is with a table. So like this. And the probability distribution table always has 2 columns or rows. And to show that, the X displays all the possible outcomes, and the second is the probability of them. So to look again here, here's the X, and here's the probability of X. And remember from the previous chapter that all probabilities are between 0 and 1. And the sum of all those probabilities in that second column in this situation, they always have to equal 1 to be a probability distribution. So here's examples of probability distribution. So here's a die roll, here's the sum of 2 die, here's a raffle prize, and you can, if you want to take the time, these all add up to 1. So the probability distribution of X says how the total probability of 1 is distributed among all various possible X values. Cal Poly Department of Statistics has a lab of 6 computers reserved for stat majors. X denotes the number of these computers that are in use at a particular time of day, and the possible X values are 0, 1, 2, 3, 4, 5, and 6. And the probability distribution will tell us how the probability of 1 is subdivided among these possible values, and how much probability is associated with the X value 0, 1, and so on. So how much probability is associated with X value 0? So X, when X equals 0 is 5%. When X equals 1, so the number of computers that are available, or that are in use, are 10%. And then when there's 2 computers in use, that's about 15% of the time, and so on. You can see how you can read that. So I would like for you to pause the video and figure out whether each of these are a probability distribution. And the tip is, these all must add to 1, or they all must be between 0 and 1. Alright, so for this first one, 2 things. Well, there's a negative probability that cannot happen, and this one is not equal to 1, the sum of all these probabilities. So that one tells you. So this next one, they're all between 0 and 1, but do they add up to 1? I do not think so. Oh, they do, if you add them up in your calculator. And then this last one, well, this one is above 1 probability, so this is not a probability distribution. For patients making appointments to have their blood pressure checked at a clinic, let X be the number of them that have high blood pressure, and the probability distribution of X is this. So using this table, we can, using the rules from chapter 5, I would like for you guys to do A, B, and C, and then I'll walk you through it on the Word document. So for A, probability of 2 or 3, well, these are mutually exclusive because they just are. So the probability of 2 or 3 is remember this rule, probability of 2 plus probability of 3, and that equals 0.27, 0.27 plus 0.08, and that equals 0.35. Probability of P more than 1, so I'm going to put greater than 1. Well, there's two ways to do this. You could 1 minus probability of 0 or 1, and that's 1 minus probability of 0 plus probability of 1, and that equals 1 minus 0.23 plus 0.41, and that equals 1 minus, let me bring up the calculator, plus 0.41, 0.64, and that equals 0.36. And the other way to do this is just simply add up the ones that are greater than 1. So, probability of 2 plus probability of 3 plus probability of 4, and then it equals 0.27 plus 0.08 plus 0.01. Then to bring up the calculator one last time, well, another time, 0.27 plus 0.008 plus 0.01, and that equals 0.36. And you see how we got the same answer in both cases? So there's two ways to do that. And then for C, probability of at least 1. So what that means is it could be 1, 2, 3, 4, and there's two ways you could do this, and that's just using the complement rule like we did in B, and that's just 1 minus probability of 0, 1 minus probability of 0 is 1 minus 0.23, and that equals 0.77. Or you could add them all up. Probability of 1 plus P of 2 plus P of 3 plus P of 4. And that equals 0.41 plus 0.27 plus 0.08 plus 0.01. And if we pull up the calculator, well, it's going to equal 0.77. But to work it out in the calculator, 0.41 plus 0.27 plus 0.08 plus 0.01, 0.77. All right. And then this is how they worked it out. And you can see this all matches up with what I have. So, calculating discrete probabilities from a distribution table, the probability of 5 less than or equal to x, which is less than or equal to 7, well, that includes 5, so it's 4/6 plus 5/6, so probability of 5 less than or equal to x, less than or equal to 7, that equals, because we want to include the x here, 4/36 plus the 5/36, because 6 is included, it's between 5 and 7, plus the 7, when x equals 7, it's 6/36, and that equals 15/36. But for probability of 5 less than x and less than 7, well, 5 can't be included because it's not equal to x, it's just less than. So there's only one outcome that's between that, and that's 6, so that's just, let me write this down, and that just is 5/36 right there. And you can see it in the work right there too, but I thought I'd work you through it. So creating a probability distribution, you roll a fair 6-sided die. You win $10 if you roll a 5 or a 6. You lose $5 if you roll a 1. And for any other outcome, you win or lose nothing. So create a table. I'm going to, please pause the video and create a table showing the probability distribution for the amount of money you won playing this, or you win playing this game. Alright, so here's the table. When x is $10, you have a 2/6 probability of winning, because you can roll a 5 or 6, and that's 2 out of the 6 outcomes. And you lose $0 or win $0 for 3 of the 6 numbers on the 6-sided die, because 2, 3, and 4 have nothing to them. And then you lose $5 when you roll a 1, and that's how you obtain this -5 for x and the probability of 1/6. So an airport parking facility contains 1,000 parking spaces. Of these, 142 are covered long-term spaces that cost $2 per hour. 378 are covered short-term spaces that cost $4.50 an hour. 423 are uncovered long-term spaces that cost $1.50 an hour, and 57 are uncovered short-term spaces that cost $4 per hour. A parking space is selected at random. So let x represent the hourly parking fee for the randomly sampled space, and find the probability distribution of x. So to walk you through this, the x is going to be like $2, $4.50, $1.50, or $4, and I would prefer if you would sort them. And then the probability of these are just whatever these numbers are divided by the total, which is 1,000. So this would be, for $4.50 it would be 0.423, for $2 an hour it'd be 0.378, and so on. And then here's the probabilities. And then here's the table. And that's what I was talking about when I was guiding you through. So examples of probability distribution graphs. Here's these are both discrete examples. So 0 for female, and the probability of the class being female is 40%, and then for the males it's 60%. And then these are the probabilities of rating on a product, let's just say. So this certain product has one star rating, 30% of them of the reviews are 1 star, and so on. So another example of a PDF is if 1/3 of the population is Hispanic and 20 randomly selected people from the population are chosen, then the PDF for the number of Hispanics is this. So they can get quite complicated, and you would never have to do anything like this above. So that does it for discrete probability distributions, and the next video I'll be talking about continuous probability distributions.